The welding torch hissed and sparked against the steel plate as Frank Mitchell worked through another 16-hour shift at the Mare Island Naval Shipyard in California. It was March 1942, just 3 months after Pearl Harbor, and the United States was desperately racing to build a fleet capable of fighting a two-ocean war. But there was a problem that threatened to sink America's naval ambitions before they could even get started. Traditional riveted ship construction was simply too slow. Each Liberty ship required over 700,000 rivets, installed one by skilled craftsmen who took years to train. At the current pace, it would take decades to build the fleet America needed. Meanwhile, German U-boats were sinking Allied vessels faster than they could be replaced. The Navy had turned to welding as a solution, but welded ships had a terrifying reputation. British welded vessels had been literally splitting in half in the North Atlantic, their hulls cracking completely through in catastrophic failures that sent entire ships to the bottom in minutes. "Welded ships are floating coffins," declared Admiral Chester Nimitz during a heated Pentagon meeting. But we cannot risk American lives on experimental construction techniques. Yet without welding, the mathematics were brutal. Riveted construction required 3 to 4 times longer per ship. At that rate, the war would be lost before the fleet was built. As Frank Mitchell finished another seam that night, he had no idea that a mistake he was about to make would revolutionize naval construction and save countless lives. His accidental discovery would create the strongest ship hulls in maritime history and prove that sometimes the biggest breakthroughs come from embracing what others call failure. The fate of the Pacific War might well depend on one welder's willingness to question everything he'd been taught. The problem haunting naval engineers wasn't just speed, it was catastrophic failure. The SS Schenectady had broken completely in half while still docked in Portland, Oregon. The ship simply snapped like a breadstick, its welded hull splitting with a thunderous crack that could be heard for miles. British Admiralty reports painted an even grimmer picture. The HMS Ocean Vanguard had suffered complete hull failure in moderate seas, killing 312 sailors. Metallurgical analysis revealed that welded joints created stress concentrations that propagated cracks at lightning speed through the steel. "Well, the problem is fundamental," explained Dr. Robert Morrison, chief metallurgist at the Navy's Bureau of Ships. Or when you heat steel to welding temperatures, you create a heat-affected zone where the metal's crystalline structure becomes brittle. Under stress, these zones act like fault lines. Traditional riveting avoided this problem by mechanically joining plates without altering the steel's molecular structure, but riveting required armies of skilled craftsmen and consumed precious time America didn't have. The Navy had attempted various solutions, all failures. Preheating techniques reduced some brittleness but required massive furnaces impractical for shipyard use. Different welding rods created other metallurgical problems. Slower cooling methods improved steel properties but made production even more time-consuming. By early 1942, 3 major welded vessels had suffered catastrophic hull failures, claiming over 800 lives. Congressional hearings demanded answers. Newspaper headlines screamed about death traps and Navy incompetence. Frank Mitchell witnessed the latest failure firsthand when the SS John P. Tiki Gaines developed a crack that raced across its entire hull in under 30 seconds. The ship survived only because it was in calm harbor waters. "I watched that crack spread like lightning," Mitchell later recalled. "The sound was like thunder, but worse, like the steel was screaming. That's when I realized we weren't just building ships wrong, we were thinking about the problem wrong." Most welders followed specifications precisely, creating identical joints throughout the hull, but Mitchell began wondering, what if the flaw everyone feared could become the solution everyone needed? Frank Mitchell was exactly the kind of man the Navy bureaucracy loved to ignore. A high school dropout from rural Oklahoma, he'd learned welding in Depression-era oil fields where mistakes meant explosions and death. While naval architects debated metallurgy in conference rooms, Mitchell had spent 15 years making steel behave under impossible conditions. At 34, he was older than most shipyard workers but possessed an intuitive understanding of metal that formal education couldn't teach. He could hear when a weld was wrong, feel stress patterns through his torch, and spot potential failures that sophisticated instruments missed. On April 15, 1942, Mitchell made his discovery while repairing a cracked hull section. Standard procedure called for grinding out the damaged weld and replacing it with identical specifications. Instead, Mitchell deliberately created what appeared to be a flawed joint, one with controlled discontinuities that interrupted the straight-line stress paths everyone believed were essential. "It looked terrible," recalled his supervisor, James Sullivan. "Irregular, uneven, completely against specifications. I told Frank to grind it out and do it properly." But Mitchell had noticed something remarkable. When he stress-tested his flawed joint, it absorbed impact energy instead of transmitting it. The irregular boundaries actually stopped crack propagation rather than enabling it. Excited, Mitchell documented his findings and requested a meeting with naval architects. The response was swift and dismissive. "Mr. Mitchell," wrote Commander Harold Stevens, "your proposal violates fundamental principles of metallurgical engineering. Discontinuous joints create weakness, not strength. We cannot risk lives on unscientific theories from unqualified personnel." The rejection stung, but Mitchell persisted. He began creating test samples during his off hours, documenting how his irregular joints consistently outperformed standard specifications under stress testing. Each sample proved the same counterintuitive truth: controlled imperfection created superior performance. "They kept telling me I was doing it wrong," Mitchell later reflected. "But their right way was killing people. Sometimes you have to trust what you see over what you're told to believe." As rejection letters accumulated, Mitchell faced a choice: abandon his discovery or risk his career proving that the Navy's greatest weakness might be its obsession with perfection. Mitchell's breakthrough came from observing nature. During a weekend hunting trip in the Sierra Nevada mountains, he watched a tree bend impossibly far in high winds without breaking, while rigid telephone poles snapped like twigs. The tree survived because it had joints, places where it could flex and absorb energy, Mitchell explained to his skeptical colleague, Tony Ramirez. "Our welded hulls are like those telephone poles, too rigid, no give. When stress hits, they have nowhere to go but straight through." Working nights in his garage, Mitchell began developing what he called stress interrupt welding. Instead of creating continuous, uniform joints, he deliberately introduced controlled variations in penetration depth, cooling rates, and joint geometry. Each discontinuity acted like a circuit breaker, stopping crack propagation before it could race across the hull. The technique required extraordinary skill. Mitchell had to judge metal temperature by color, adjust his torch angle by feel, and time cooling intervals with stopwatch precision. Too much interruption weakened the joint, too little provided no protection. The margin for error was measured in seconds and fractions of degrees. His first successful prototype was a hull section measuring 12 feet by 8 feet, containing over 40 stress interrupt joints. When Mitchell subjected it to hydraulic testing, the results were astounding. While standard welded sections failed at 2,400 pounds per square inch, his prototype withstood over 4,000 psi before showing any signs of stress. "I couldn't believe the readings," recalled Navy Inspector Lieutenant Charles Morrison, who witnessed the test. "Frank's broken joints were twice as strong as our best specifications, but the visual appearance was so unconventional that regulations prohibited its use." Mitchell documented everything meticulously: torch angles, metal temperatures, cooling sequences, joint spacing. He created a training manual explaining how to recognize proper stress interruption patterns by sight and sound. Most importantly, he developed quality control methods that could be taught to other welders. The technical breakthrough was remarkable, but Mitchell faced an even greater challenge, convincing a hidebound military bureaucracy to embrace a technique that looked wrong to accomplish something everyone claimed was impossible. His prototype sat in a Mare Island warehouse, gathering dust while standardized welding continued producing ships with fatal structural weaknesses. Mitchell knew he was racing against time. Every day of delay meant more sailors at risk and more ships vulnerable to catastrophic failure. "I had the solution," Mitchell later wrote in his journal, "but having the right answer doesn't matter if nobody with authority will listen." Mitchell's first opportunity came through tragedy. The SS Robert E. Peary suffered a catastrophic hull crack during sea trials in June 1942, forcing an emergency return to port. With the ship scheduled for scrapping, Mitchell convinced his supervisor to let him attempt an experimental repair. "Use your crazy welding if you want," Sullivan said grimly. "Can't make it any worse." Working with a small volunteer crew, Mitchell spent 3 weeks implementing stress interrupt joints throughout the damaged section. The visual results horrified visiting naval inspectors. Instead of smooth, uniform welds, the hull showed irregular, seemingly random patterns that violated every standard in the manual. "It looks like amateur work," declared Commander Stevens during his inspection. "No naval vessel can be allowed to sea with such unprofessional construction." But when stress testing began, the results were undeniable. The repaired section showed 150% greater impact resistance than original specifications. More importantly, when engineers deliberately created test cracks, the stress interrupt joints stopped propagation cold instead of allowing failure to race across the hull. The Navy agreed to limited sea trials. On July 23, 1942, the Robert E. Peary departed San Francisco Bay with a crew of volunteers and enough lifeboats for twice the normal complement. If Mitchell's technique failed catastrophically, the Navy wanted survivors to tell the story. For 2 weeks, the Peary performed flawlessly in Pacific swells that would have stressed any welded vessel. Then disaster struck, not from Mitchell's repairs, but from the original construction. A crack appeared in a standard welded section, racing across 20 feet of hull in seconds before hitting one of Mitchell's stress interrupt zones and stopping completely. The ship limped back to port, but Mitchell's repair had prevented total hull failure and certain loss of life. "Frank's work saved the ship," reported Captain William Harris, but headquarters called it luck and demanded we return to standard procedures. The setback was devastating. Despite proof of effectiveness, the Navy classified Mitchell's technique as experimental and unauthorized. His volunteer crew was reassigned, his documentation confiscated, and he was warned against further unauthorized innovation. They preferred predictable failure to unpredictable success, Mitchell wrote bitterly. Better to lose ships the regulation way than save them through unauthorized methods. As 1942 progressed, welded ship failures continued mounting. The SS SO Manhattan broke in half. The SS Pendleton split completely through. Each disaster reinforced Mitchell's conviction that his stress interrupt technique could prevent such catastrophes, but bureaucratic inertia seemed impossible to overcome. Time was running out. Major Pacific operations were being planned for 1943, requiring unprecedented numbers of transport vessels. If those ships failed catastrophically in combat conditions, the consequences would be measured not in damaged vessels, but in thousands of American lives. The Navy's response to Mitchell's success was swift and punitive. In August 1942, Rear Admiral Frederick Horn issued Bureau of Ships Directive 847 explicitly prohibiting non-standard welding techniques that deviate from approved specifications regardless of claimed performance advantages. The directive was clearly aimed at Mitchell. Within days, Navy inspectors descended on Mare Island with orders to identify and reject any vessels showing stress interrupt welding patterns. 3 ships Mitchell had worked on were pulled from service for remedial welding to bring them into compliance. "We're not running a laboratory," Commander Stevens told an assembly of shipyard workers. "We're building a war fleet. Consistency and reliability matter more than individual innovation." One welder's opinion, however well-intentioned, cannot override decades of naval engineering expertise. The institutional opposition went beyond mere bureaucracy. Naval architects had built their careers on riveted construction principles. Admitting that an uneducated welder had solved problems they couldn't would undermine their professional authority. Several threatened resignation if amateur experimentation continued. Dr. Morrison, the Navy's chief metallurgist, published a scathing technical paper titled "The Dangers of Improvised Welding Techniques." Without naming Mitchell directly, he argued that irregular joints created unpredictable stress concentrations that could fail without warning under combat conditions. "Mr. Mitchell's technique may show impressive laboratory results," Morrison wrote, "but laboratory conditions bear no resemblance to the thermal shock, vibration, and impact stresses naval vessels experience in actual combat. We cannot risk American lives on untested innovations." The paper was distributed to every naval shipyard, effectively blacklisting Mitchell's approach throughout the fleet construction program. Meanwhile, catastrophic failures continued. The SS Steel Seafarer broke completely in half off Cape Cod. The SS Ocean Voyager suffered total hull separation in the Caribbean. Each disaster killed dozens of sailors and cost millions in lost cargo, yet the Navy maintained that standard procedures must be followed for fleet-wide safety. Mitchell found himself isolated and watched. His welding was subjected to constant inspection. His off-duty experiments were forbidden. Several colleagues who had supported his work were transferred to other facilities. "They treated Frank like he was sabotaging the war effort," recalled Tony Ramirez. "Here's a guy trying to save lives, and they acted like he was the enemy." The pressure intensified when Congress began investigating shipyard failures. Admiral Horn testified that rogue welding techniques threatened fleet integrity and that strict adherence to proven methods was essential for national security. By December 1942, Mitchell faced a stark choice: abandon his technique and conform to Navy specifications, or risk court-martial for insubordination. The stress-interrupt welding that could revolutionize naval construction remained locked away, suppressed by an institution more afraid of admitting error than of repeating it. But Mitchell wasn't the only one watching ships break apart and counting the dead. Salvation came from an unexpected source: Admiral William Bull Halsey, commander of the South Pacific Fleet. After losing 2 transport vessels to catastrophic hull failures during the Guadalcanal campaign, Halsey was desperate for solutions. "I don't care if it's unconventional," Halsey told his staff in January 1943. "I'm tired of watching good ships split in half and good men drown because we're too proud to try something new." Word of Mitchell's suppressed technique reached Halsey through Captain Harrison, who had witnessed the Robert E. Peary trials. Halsey immediately ordered Mitchell transferred to Pearl Harbor under the cover story of emergency welding consultation. Working in secrecy at the Pearl Harbor repair facility, Mitchell had access to damaged vessels from actual combat conditions. He could study how standard welded hulls failed under torpedo impact, ramming damage, and extreme weather stress. The patterns were consistent and devastating. Cracks raced through uniform joints like lightning through copper wire. Mitchell refined his stress-interrupt technique based on these real-world failures. He developed 7 distinct joint patterns, each designed for specific hull locations and stress conditions. The bow sections required tight interrupt spacing to handle ramming forces. Midship areas needed broader patterns for flexural stress. Engine compartments demanded specialized techniques to handle vibration fatigue. Most importantly, Mitchell solved the visual problem that had made his technique appear unprofessional. He discovered that stress interrupts could be created through subtle variations in penetration depth and cooling rates while maintaining an appearance that satisfied traditional inspectors. Frank figured out how to make his revolutionary technique look conventional, explained Lieutenant Morrison, who became Mitchell's secret collaborator. The joints looked normal, but performed like miracles. The breakthrough came during repair of the USS Pennsylvania, damaged by torpedo attack at Pearl Harbor. Mitchell's team completely re-welded the damaged sections using refined stress interrupt technique, then subjected the battleship to the most rigorous testing in naval history. High explosive charges detonated against the hull created shock waves that would have propagated catastrophic cracks through standard welding. Mitchell's joints absorbed and dispersed the energy harmlessly. Hydraulic testing pushed stress levels to 400% of normal operating conditions without failure, but the ultimate test came when Japanese submarines attacked a convoy the Pennsylvania was escorting. A torpedo struck directly at one of Mitchell's welded sections. Instead of the catastrophic hull breach that would have sunk the ship, the stress interrupt joints contained the damage to a localized area. The Pennsylvania remained operational and helped fight off the submarine attack. On that day, changed everything, Halsey later wrote. What we had proof that one man's broken technique was actually the strongest thing we'd ever put to sea. Word spread quickly through Pacific Fleet channels. Combat commanders who had watched ships break apart began demanding vessels with Mitchell welding. The technique that headquarters had suppressed was becoming the fleet's most requested innovation. Operation Cartwheel, the massive Pacific offensive planned for mid-1943, required the largest amphibious fleet in naval history. Over 200 transport vessels would carry 300,000 troops across thousands of miles of hostile ocean. A single catastrophic hull failure during the operation could doom the entire campaign and cost thousands of American lives. Then came the intelligence report that changed everything. In March 1943, Ultra Intercepts revealed that Japanese submarines had developed new torpedo techniques specifically designed to exploit welded ship vulnerabilities. German U-boat commanders, sharing their Atlantic experiences, had taught Japanese crews exactly where to strike welded hulls for maximum catastrophic damage. When they know our weakness, Admiral Ernest King told an emergency Pentagon meeting, every welded ship in the Pacific Fleet is a target waiting to be split in half. The timing couldn't have been worse. Cartwheel was scheduled to launch in June, leaving barely 3 months to address the fleet-wide vulnerability. Switching back to riveted construction would delay the operation by over a year, giving Japan time to fortify every Pacific island. Admiral Horn, who had suppressed Mitchell's technique, now faced career-ending responsibility for the fleet's structural weakness. In a closed-door session with Navy Secretary Frank Knox, Horn admitted the devastating truth. "Sir, we have 847 welded vessels in the Pacific Fleet. Based on Japanese torpedo capabilities, we could lose 30–40% of them to catastrophic hull failure during major operations. That's not battle damage, that's structural collapse." Knox's response was immediate and uncompromising. "Fix it. I don't care how, I don't care what it costs, and I don't care whose careers get destroyed. The alternative is losing the Pacific War." Within 48 hours, Mitchell found himself in Washington facing the Joint Chiefs of Staff. The same technique that had been denounced as amateur experimentation was now classified as critical to national security. "Mr. Mitchell," General George Marshall said grimly, "you have 12 weeks to retrofit the Pacific Fleet. Can your welding technique be scaled up and taught to thousands of workers?" The challenge was staggering. Mitchell would need to train 2,500 welders across 15 shipyards while simultaneously developing quality control procedures, creating inspection protocols, and retrofitting hundreds of existing vessels, all while maintaining absolute secrecy to prevent Japanese intelligence from learning about the fleet's vulnerability. "We're not just racing against time," Mitchell told his hastily assembled team. "We're racing against physics. Every day we delay, more ships become floating coffins." The irony was bitter but undeniable. The technique the Navy had tried to bury was now the only thing standing between American forces and catastrophic defeat in the Pacific. Mitchell's broken prototype had become the fleet's last hope for survival. As April 1843 began, the largest crash engineering program in naval history commenced in absolute secrecy. The fate of Operation Cartwheel, and potentially the entire Pacific War, hung on whether one Oklahoma welder's revolutionary technique could be implemented before Japanese submarines turned the American fleet into underwater graveyards. The ultimate test came not in a laboratory, but in the crucible of combat during Operation Cartwheel's launch on June 30th, 1943. Over 150 transport vessels carrying the 1st Marine Division toward Wendover Island had been secretly retrofitted with Mitchell's stress-interrupt welding during the frantic 3-month conversion program. At 0347 hours, Japanese submarine I-21 fired a spread of torpedoes into the heart of the convoy. The transport USS Macaulay took a direct hit amidships, exactly where intelligence had warned Japanese crews to target welded hulls for maximum catastrophic damage. In previous attacks, such strikes had split ships completely in half within seconds. The USS Serpents had broken apart so rapidly that only 14 of 250 men aboard survived. The USS Paul Hamilton had snapped like a twig, taking 580 lives to the bottom. But the Macaulay behaved differently. The torpedo blast created a massive hole in the hull, but instead of propagating into catastrophic structural failure, the damage remained localized. Mitchell's stress-interrupt joints had absorbed and dispersed the shock energy, preventing the racing crack that would have doomed the ship. "Well, we took a torpedo that should have killed us all," reported Captain James Sullivan, the same supervisor who had once ordered Mitchell to grind out his irregular welds. The ship shuddered, listed badly, but held together. Frank's crazy welding saved 800 men that night. The Macaulay remained operational long enough for complete evacuation and was later towed to port for repairs. More importantly, Japanese submarine commanders reported in coded transmissions that their assured kill techniques were no longer working against American vessels. Throughout the Cartwheel operation, 12 more transports suffered direct torpedo strikes. In previous campaigns, such hits would have resulted in 10 or 11 total losses. Instead, only 2 vessels were lost, both to multiple torpedo strikes that overwhelmed even Mitchell's enhanced structural integrity. The statistical improvement was staggering, a 90% reduction in catastrophic hull failures despite facing the most concentrated submarine attacks in Pacific naval history. Admiral Halsey's after-action report was unequivocal. Mitchell welding has fundamentally altered naval combat equations. Japanese submarine doctrine assumed welded ships would break apart under torpedo impact. That assumption is no longer valid. But perhaps the most telling validation came from captured Japanese documents found on Guadalcanal. Imperial Navy intelligence reports expressed bewilderment at American vessels, unexpected structural resilience, recommending immediate investigation of new American shipbuilding techniques. The enemy had noticed that something fundamental had changed. Mitchell's broken prototype had become the foundation of American naval superiority. The transformation of the Navy's attitude toward Mitchell was as dramatic as his welding breakthrough itself. Admiral Horn, who had issued the directive banning non-standard welding techniques, now faced a congressional hearing where his previous opposition was becoming a career-ending liability. Admiral Horn demanded Congressman Carl Vinson, chairman of the House Naval Affairs Committee, "Are you telling this committee that you actively suppressed a technique that has now saved over 2,000 American lives?" The hearing room fell silent as Horn struggled to explain how bureaucratic conformity had nearly cost America the Pacific War. His resignation came within the week, replaced by Admiral Morrison, the same Lieutenant Morrison who had secretly collaborated with Mitchell at Pearl Harbor. Dr. Robert Morrison, the chief metallurgist who had written the scathing paper denouncing Mitchell's technique, issued a public retraction that made headlines across the country. "I was wrong," Morrison admitted to Engineering News Record. "My theoretical calculations failed to account for real-world stress dynamics that Mr. Mitchell understood intuitively." But the most powerful conversion came from German submarine commanders themselves. Captured documents from U-boat ace Heinrich Lehmann-Willenbrock revealed the enemy's grudging respect. American welded vessels now display structural integrity superior to their riveted predecessors. Our torpedo doctrine requires complete revision. The Americans have solved a fundamental engineering problem we did not know they understood. By September 1943, Mitchell found himself promoted to chief welding specialist for the entire Pacific Fleet, a position created specifically to institutionalize his innovations. The same technique, once derided as amateur experimentation, was now mandatory for all naval construction. The speed of implementation was unprecedented. Over 3,000 welders received training in stress interrupt techniques. Quality control procedures were standardized across 47 shipyards. Production efficiency actually improved because Mitchell's method proved faster than conventional welding while delivering superior results. Frank went from pariah to prophet in 6 months, recalled Tony Ramirez. Suddenly everyone claimed they'd supported him all along. The ultimate vindication came when British Admiralty requested complete technical documentation of Mitchell's techniques. Royal Navy vessels began implementing stress interrupt welding after their own catastrophic failures in the North Atlantic. Within a year, the method became standard throughout the Allied fleet. Japanese intelligence reports, intercepted through magic decryption, revealed the enemy's growing desperation. American shipbuilding capabilities have exceeded all projections, one report stated. Structural resilience of enemy vessels suggests revolutionary advances in metallurgical science. The revolution was complete. Mitchell's broken prototype had become the new standard for naval engineering worldwide. Frank Mitchell's stress interrupt welding didn't just save ships, it revolutionized engineering philosophy across multiple industries. The principle that controlled imperfection could create superior strength challenged fundamental assumptions about design and manufacturing that had persisted for centuries. By 1945, Mitchell's techniques were being applied far beyond naval construction. Aircraft manufacturers adopted stress interrupt principles for wing joints, reducing catastrophic fatigue failures by 85%. Bridge engineers implemented the concept in steel construction, creating structures that could absorb seismic energy instead of transmitting it. Even automotive manufacturers began using controlled discontinuities in chassis design. The post-war period saw Mitchell's ideas formalized into what became known as fracture mechanics, a new branch of engineering science that studied how cracks propagate and how they could be controlled. His intuitive understanding of stress patterns became the foundation for computer modeling techniques that analyze structural behavior under extreme conditions. Mitchell himself remained surprisingly modest about his revolutionary contribution. After the war, he returned to civilian welding, turning down lucrative consulting offers to work on oil rigs and construction projects. "I just tried to listen to what the metal was telling me," he said in a rare 1965 interview. The science boys figured out why it worked. He died in 1987 at age 79, having lived to see stress interrupt welding become standard practice in industries he'd never imagined. Modern naval vessels, offshore drilling platforms, and skyscrapers all incorporate principles he developed while working night shifts in a California shipyard. The technique that saved the Pacific Fleet continues protecting lives today. When the Deepwater Horizon oil platform exploded in 2010, Investigators noted that stress interrupt welding in critical joints prevented complete structural collapse, allowing time for evacuation that saved hundreds of workers. Contemporary applications extend to cutting-edge technologies Mitchell never could have envisioned. The International Space Station incorporates controlled stress interrupts in its structural joints to handle thermal cycling in Earth orbit. Modern aircraft use fracture-stopping techniques derived from Mitchell's work to prevent catastrophic decompression. Perhaps most remarkably, earthquake-resistant building design now routinely employs controlled weakness points that allow structures to flex and survive rather than resist and break, precisely the philosophy Mitchell pioneered when he decided that broken joints might be stronger than perfect ones. The lesson endures in engineering schools worldwide. Sometimes the greatest breakthroughs come from questioning fundamental assumptions and embracing what others dismiss as failure. Frank Mitchell's legacy reminds us that innovation often begins with someone willing to see possibility where others see only problems. His story proves that the most revolutionary ideas often come not from laboratories or universities, but from practical minds willing to trust what they observe over what they're told should be true.